Welcome everyone. So, in this lecture we will look at auto-regressive models. So, we are discussing generative models so far and looked at the adversarial networks and variational autoencoders. Now, in this series the last family of models that we will be looking at are auto-regressive models. These are also generative models. So, these are the ones that are powering the modern day LLMs, large language models mostly. Okay. There are another family of models called state space models which are an alternative to auto-regressive models. They are not mainstream yet in the sense that most of the production grade LLMs are based on auto-regressive models. So, we will look at what auto-regressive models is in the first half of the class. In the later half we will also look at, I will introduce you to the idea of reinforcement learning. So, RL. So, what is the broad idea of RL is? See, RL is a topic which can be taught as a full course one semester, but I will just introduce you to RL as a paradigm. Okay. So, auto-regressive models are defined this way. So, the topology that we consider when we look at auto-regressive models is where the data is sequential in nature. It does not have to be. So, we already saw how to represent different data topologies as sequences, right. I mean you can view a natural language paragraph as a sequence. You can also view image as a sequence, right. So, you take every patch and arrange them and that becomes a sequence and so on. So, assuming that the data is sequential in nature, auto-regressive models best fit into such a kind of a data topology. Now, we do the analysis for a single data point. Let us say that you have one data point that has t number of tokens. So, now the terminology that we were using when we looked at transformers as an architecture, right, holds true here as well. So, every data point has capital T number of tokens. So, every of this token is a d dimensional vector. So, you have a d by t matrix. You can represent every data point as a d by t matrix where you have capital T number of vectors, each of dimensions d stacked into a series. So, that is one data point. Okay. Examples are natural language sentence and multivariate time series and so on. So, where every word can be looked into as one member of this sequence. Okay. Now, the goal for any of the ML problem is to estimate the underlying distribution, right, and especially for generative models we also want to understand how to sample from the distribution. So, an auto-regressive model would help do both. So, it will help you model the underlying distribution and also give a way to sample from it. Yeah, we have already seen this, right. Solution is to parameterize Px using some parametric family of distributions P theta and learn the parameters of P theta by optimizing it in the divergence measure. This has been the central theme of the entire course that we have seen so far. And of course, mathematically speaking, you take KL divergence and find out theta star that would minimize the KL divergence or equivalently maximize the expected log likelihood. So, that is what we wanted to do. So, auto-regressive models, see every model we have seen what a model is, right. A choice that we make to P theta is what we call as a model. So, what sort of, that is why neural network is a model, kernel machine is a model and so on. What is changed? What changes is this P theta, correct. Now, in auto-regressive model this is how P theta is written. Now, P theta of the entire sequence, so which is a single data point, is given as the product of these many conditional distributions, okay, where each of the conditional distribution is a distribution over one time step, okay, conditioned on everything that is before that particular time step. See, the notion of before or the temporal notion of a sequentiality is only notional. So, what do I mean by that is that if you take a sentence, the words have a temporal notion to it, right. I mean a given word precedes a particular word and so on. But if you express an image as a sequence, then there is no notion of temporal sequentiality anyway. But there is still, I mean you can, if you consider different patches as different tokens, you can see that, you can say that one patch is coming before the previous patch or the current patch and so on. So, there is the notion of sequentiality is assumed to be in data inherently. So, these distributions are P theta of xt where xt is the tth token conditioned on everything that is occurring before t. Okay. So, now this is simply, so what is this? This is simply the chain rule of probability, right. You have capital T number of random variables, then the joint distribution of all those can be written in terms of product of multiple conditionals, where you take the first random variable, condition it on everything that is before that, and so on. So, this is the definition of what an auto-regressive model is. The name auto-regression is coming from the fact that every random variable at a given temporal step is being modeled as a function of everything that occurs before that in the same sequence. So, it is regressing over itself, that is why the name auto regression. So, you can look into this as as regressing over every step of the sequence, okay, depending upon or as a function of everything that occurs before it. Okay, this is the most general form of an auto-regressive model, and there are multiple examples of auto-regressive models. There are classical examples and neural examples and so on. Just state a few. One historical classical example of an auto-regressive model is what is called as, what is actually referred to as an AR. Have you heard of these things called ARMA model and so on? Auto-regressive and moving average models and so on, right? I mean, comes in classical control theory and signal processing, where this is the definition, right. You consider, you express xt, which is the tth token, as simply a linear combination of all the tokens that are coming before that. So, where AIs are learnable model parameters. So, this is how you represent a classical auto-regressive model. Okay. And there are neural auto-regressive models where each of these constituent distributions here, p theta of xt conditioned on x, everything that is before t, each of those distributions are modeled using neural networks. Okay. So, this is where neural language models, and by the way these are also called language models. This auto-regressive model is the go-to choice for language modeling, because if you are, the underlying distribution, underlying data can be seen as natural language, and what you are actually modeling is the underlying language, and that is why they are called language models. Okay. Now, neural language models or neural AR models are where these constituent distributions are modeled using neural networks. So, what do you mean by that? There is an MLP. MLP takes all tokens till t as an input, okay, and predicts the tth token, that is it. So, it is simply an MLP that regresses over the tth token by taking every token before the tth token as an input. Do you see that? So, what happens is the tokens that go as an input to this neural network changes at every time step, but that is okay. I mean, you are simply regressing it on the tth token depending, I mean, based on every observation that you have made till the tth token. That is a neural language model. In fact, this was one of the very early models of language that used neural networks. I think Yoshia Bengio and his colleagues came up with this idea of neural language models. See, then people said that using an MLP for this is not a great idea, because the sequentiality is totally lost, because every token before t, see, if you express all tokens before t as random variables and as vectors and just stack them all together and give it as an input to an MLP, the idea of sequentiality is lost, because it does not matter, right. I mean, MLP does not implicitly have this idea of sequentiality. So, then people move to recurrent architectures, okay, where p theta of xt given x less than t is modeled using RNNs, right. So, now we know how to use an RNN, right. So, this RNN takes everything from x0 to xt minus 1 as an input, and what it predicts is xt, the tth token. So, it is a proper RNN. So, then the idea of sequentiality is still intact. That is how the field progressed. So, initially they were all deterministic models, and then people moved to, I mean, there is, okay, I think before neural models, right, or maybe concurrently, people also looked at what are known as Markov models for language models, right, bigrams and trigrams and so on, where you model these distributions using Markov chains. You say that given given xt minus 1, the dependence on xt is only on xt minus 1 and not anything before it. It is a first order Markovian model. Those are called bigram, trigram and so on. Bigram is dependence on the previous 2 tokens, trigram is dependence on previous 3 tokens and so on, and then you take ML estimates for each of the individual distributions, that is it. So, they are bigram, trigram language models. Then came neural language models, then people started using recurrent neural models, LSTMs and so on. And then came, I mean you know all these problems, right? There is parameter sharing across time, and you have LSTMs, and you know all that you did in your second assignment, and you have the problem of vanishing gradients and so on. And then people came up with this idea called attention mechanism, right? So, you have a very long sequence, and there is the final hidden state was burdened with compressing all the information. So, people said, why do you want to take that final hidden state? Why do not you tap the information from each of the intermediate hidden states and take a linear combination of it and give it to the output. That is the idea of attention, right. So, you can have the attention mechanism on top of an RNN, we saw all this. So, then came this paper, right, attention is all you need, where the recurrent architecture was completely taken off, and a new architecture called transformers was introduced, where you only have attention mechanism followed by MLP and so on. So, we have seen all that. Okay. So, now so I will skip all this because we did this attention mechanism and so on. Now, assuming that we already know what transformers are, which we do. Now, an auto-regressive generative model is where the underlying probability distribution for a sequence is still auto-regressive. Okay. However, p theta of x t given x less than t, okay, is modeled using a transformer, that is it. So, that is what modern day LLMs are all about. Now, they are auto-regressive generative models, okay, with p theta being estimated using or expressed using this particular auto-regressive formula, and the individual distributions that come within this product are modeled using transformers. Okay. See, by the way, to be technically precise, any model that adheres to this particular mathematical formula is referred to as an auto-regressive model, but you can use transformers to express these distributions, and if you do, I mean that is what the modern day LLMs do. Okay. So, large language models are auto-regressive models with p theta of x t given x less than t being expressed using transformers, that is it. Any questions so far? There is actually one question that still lingers, which I have not answered, right. How do you ensure that a transformer only regresses on the previous tokens given a current token? That we have not seen, right, yet. These are called causal transformers. I will just talk about it in a while. I mean, if except for that question, if there is any other question, I will take it now.
Generic standpoint, when we are saying that we are modeling the distribution using any of the architecture. So, we are meaning that these architectures are actually formulating the parameter of the distribution, right? Whichever distribution we want, it will be into the last function. If we take
that is correct. See, the thing is, but these are implicit. Most of the neural architectures, most of the neural architectures are implicit in the sense that you do not have an external parametric distribution that you assign to and then estimate the parameters, unlike in let us say the ML estimation. So, there you assume your p theta to be a Gaussian distribution and then estimate the parameter, but in all the non-parametric implicit distribution estimators like neural networks, you assume that the distribution is implicitly being modeled using the neural network, that is it. But I mean, as I mentioned in the last class also, right, the moment you say that the output, the loss function is let us say cross entropy, you are assuming that the distribution of the final layer follows a Bernoulli distribution, okay, whose parameter is what you are modeling using this entire function called neural network. So, that is anywhere there. I mean, of the distribution of the random variable that you obtain at the final layer of the neural network, right. So, that is how it is. Any other question? Okay. Now, we will have to see how to use transformers to model this p theta of x t given x less than t, right. So, as I said, given a data matrix denoted by capital X. So, what is this data matrix? Arrange all of these tokens, okay, in a matrix. So, you have capital T number of them and each of them has dimensions d or dm, Okay. So then we have this attention mechanism, right. So as I am assuming that all of we know this, right, compute the attention mechanism. And what does this attention mechanism actually do? We see this attention mechanism as a latent variable model as well. Have I told you this view? Attention transformer is attention mechanism is also a latent variable view, right, where you have linear projections of data. Given data in x t cross dm dimension, it projects it onto some other space which is t cross dv dimensions, okay, and the z is simply given by this particular operation, right, softmax of qk transpose divided by root of dk, and yeah, you get the projections of data. So that is what this attention. So what happens is, starting from a t cross dm matrix, you get a t cross dv matrix. So it is just your data got projected onto a particular space, which are defined by these matrices, the wq, wk and wb matrices that we have seen. So then to ensure that see, right now there is no causality here yet. The auto-regressive models are causal by construction. What do you mean by that? The dependence of xt is only on its previous tokens, okay, not the future tokens. So, but right now the way we have defined transformers, the causality is not embedded onto the model, right, it is not causal. So, we will have to ensure that the causality is embedded onto the model. So, how do we do that? There is something called causal masking or causal attention. It is a pretty simple idea. So, to ensure that xt depends only on the previous tokens and not on the future tokens, attention mechanism has to be modified this way. So, define a matrix of size t cross t, there are t number of tokens, define a matrix of size t cross t, and the ij element of this matrix is as follows. If it is 0, okay, if j is less than or equal to I, it's minus infinity if it's greater than I, if j is greater than I. Okay, what do we do? Remember that the attention mechanism, after the dot product between the query and key values, before you multiply it with the value vectors, take the linear combination, you will have to pass it through the softmax to ensure that the values are bounded between 0 and 1, right. Now before you pass it through the softmax, just add this masking matrix. Now what does it do? Softmax has an exponentiation operation to it, right. So m has 0 for it's a diagonal matrix. Can you see that this is a diagonal matrix? Is it sorry, it's a triangular matrix, it's a triangular matrix, right. So because it's a triangular matrix, whenever j is greater than I, where the dependence is on future, it will pull all those values to 0 because m is minus infinity in those things, and e power minus infinity goes to 0, and for the other values it doesn't touch that. This is called causal attention mask. So if you do this, then the corresponding z's that we get by passing by doing causal attention are by construction auto-regressive. So by doing this, you are modeling p theta of x t given dependence is only now on every t that is less than t. Does it make sense? That is it, yeah.
I understood what you did there mathematically, but I don't understand why adding m captures that causal relationship, causality relationship that you're talking about.
No, it does not. See, all this m does is that the dependence on xt is only on everything that is coming before xt is what it ensures. That is it. So see, there is no explicit causal regularizer that we are putting here. We are only saying that xt can only depend on everything before that. The only regularization that we are doing here is we are killing the dependency of xt on everything that occurs later, correct. And also remember that we have positional embeddings here. Because we have positional embeddings with the transformer, we are explicitly telling transformer what the sequentiality is. You remember positional embeddings, right? Otherwise even transformer does not have the idea of what precedes what and what succeeds what, and we are explicitly hard coding it by adding the positional embedding, right. So by this regularization, what we are doing is we are stopping transformer from looking at everything that comes after t, that is it. What happened? Okay, so did I talk of multi-head attention? Did I? Okay, so yeah, so it is done now, and then we have fully connected layer and so on. and yeah. So finally this is how a transformer looks. So just for the sake of completeness, I think I have drawn this as well, right? Yeah. So this is how it is. You start with X and there is you have input embeddings to start with, and then we have multi-head attention blocks, and then you have fully connected layers, and finally we have a linear and a softmax layer, and at every softmax is over the entire dictionary from which we are getting our token. So it will give you a probability distribution over the entire dictionary, right. So now how did this become yeah, so how do you train this? You have a sequence of tokens, okay, x1 through xt, and we have assumed an autoregressive formulation here, okay, and this comes up because there is causality. P theta of xt given x less than t is taken to be the output of the transformer at the tth token. So what you do is take a sentence or any sequence, okay, take any tth token, okay, and give everything till t as an input to the transformer and predict the, or rather you take everything till t minus 1 and predict the tth token, that is it. So this is what is uh, famously referred to as the next token prediction task, right. You can see this as supervised learning where the supervision is on the next token. Do you see this? But it is completely unsupervised because there is no sense of labels here. Also it is also self supervised because the supervision is coming from itself and so on, okay. This is how the GPTs and the Geminis and Claudes are trained. I mean at the bare bone method. So they train these LLMs, okay, using this sort of, I mean, and what this is what it is, no. You take x1 through xt minus 1 and target tokens are taken to be the next tokens, and then simply use the cross entropy because you are it's a discrete distribution at the output, right, over the vocabulary. Typical vocabulary size will be of let us say 1 or 2 million tokens, okay. And by the way, a token is not a word, I have told you already, right. I mean they do this thing called byte pair encoding, and it can be subunits of thing, I mean especially in the case of language, and then it is simply a an ERM on this architecture, and this also is implicitly a generative model, right. Why? Because during inference what do you do? Do the exact same thing. What you give as input prompt is x1 through xt, then you predict the next token, take that, append and give the entire thing to the next one and keep predicting one after the other, that is it. That is how the inference also happens, and now you know why it is a sampler also. These auto-regressive models are also samplers because I hope all of you understood what I am saying, right. During training you take these sentences, take till t minus 1, predict the tth one, and you have this entropy loss and backpropagate, that is it. During inference there is an input prompt, okay, that is your first t tokens, predict the t plus 1 and then append it, predict t plus 2 and keep doing it, that is it. The way you do it in an LSTM, same thing. When do you stop, by the way? Yeah, there is a special token called end of sentence token, right. Whenever the model outputs EOS, that is when you stop.
There is no next sentence.
Come again?
End of sentence is not literally the English.
No, end of response, right, that is what it means, right. You stop there and then give the next prompt and so on. So it is pretty amazing, and you know both amazing and disturbing that a technique that is mathematically as simple as this and elegant could actually crack intelligence. So there is nothing much to what, I mean of course I am simplifying, there is you will have to ensure that the models align with human preferences and so on, that is where we have RL that we do. But the pre-training, the model pre-training as it is called, right, unsupervised pre-training is just this, and today it is done on done over months. So people take 6 to 8 months to do this training on pretty much the entire internet, okay, and the underlying models are transformers which have billions of parameters, or rather trillions of parameters. So this is a nice end to the course in the sense that, I mean whatever we learned is just this, right. So you have data given from an underlying distribution, you have to model the distribution and learn to sample from it, and then you assume some model on top of it and then minimize the KL divergence and do that using gradient descent, that is all, that is all which is happening, okay, and of course you need to regularize it so that it does not overfit and so on. But yeah, it's maybe it's disappointing in the sense that this is all it takes to crack human intelligence, okay, but that's what is happening. So that is what the pre-training of all transformer models are. Any questions here? These are large language models, by the way, these are LLMs. We will stop here and continue in the next lecture.